כאילו, אני כותב את הפרצה של הוקטור WI שלי על ההייפרספייס הזה של כל הממדים, אז יש לי תנועה אינטנסיבית ב-N ממדים.
נכון, אז יש כאילו, כאילו, מה זה? ברור שיש לך תלות, שאתה תלוי באיזה כיוון אתה תלך, אתה בעצם...
על פי המיקום שאני...
על פי המיקום, כן, על פי המיקום שאתה נמצא, ויש לך גם תלות בעצם בשאר הכיוונים. זה כאילו, זה לא אינטנטי, זה באמת מה שזה, עכשיו זה גם קורה, הרי מאיפה מגיע לזה? אני לא יודע אם הוא דיבר על זה, כי לא הולך להגיד, אבל בעיקרון הוא מסתכל על רשתות, נוירונים. עכשיו, ברשתות, מה שאתה עושה, אתה עושה גרדיאנט דיסנט הזה, ואתה עושה את זה במיני בייסים.
כן, זה כאילו, שוחחתי שם
בדיוק. וכאילו, ואז המיני בייסים האלה, מה שאנחנו בפועל, ויש גם עבודות שמראות את זה, שבעצם, אם לא, בעצם הרעש שלך הוא בעצם, הוא לא איזוטרופי מהבחינה הזאת, נורא יפה וזה, ואז יש לך המון רעש והמון כיוונים, ולא רוצה שתלוי גם בעצם
באיפה היית לפני?
באיפה היית לפני, בדיוק. תלוי באיפה היית לפני, שזה גם הגיוני, כי תחשוב, אם יש לך אירור מאוד מאוד מסובך.
אני חושב שאני מבין את זה.
טוב, אני אשאל את נילי, אני לא יודע כך, אני אשאל את נילי מה לעשות בעניין הזה, אולי יש...
אני לא יודעת להגיד למה המבחן,
המבחן מה, זה של כל המבחנים?
במידע האישי?
במידע האישי? אני הולך לדבר עם נילי, אני אשאל אותה מה... אני יודעת משהו על זה. Okay, more problems? No? Okay. So today we are going to talk about lossless data compression and after it about channel capacity. And basically it's the same problem and we'll talk about it. So lossless data compression. The framework is that we have some source, okay? Let's write it. So we have a source X, okay, and it can get values from 1 to m, and it has some distribution p of x. Okay, and now we would like to encode this message, this source, using some alphabet with D symbols. Okay, so we have some alphabet sigma. Okay, with D symbols. Now we want to map each value of x to some code word in sigma, but not to sigma, but to sigma star. What is sigma star? Basically, it's just the union of all the lengths of sigma. Okay, so sigma star is the union of all the sigmas, all the length of sigma. So, for example, if sigma is 0 and 1, then sigma star will be all the possible strings of zeros and ones. Okay. So we have sigma star, and we have now the code because we want to encode our source. So we say that C is a D-array code if it's a map from X to sigma star. Okay? Yeah.
So sigma star is a sequence of the objects in sigma up to order n. That's what you.
No, no. So sigma to the power of n. So sigma n is exactly the number is, for example, 0 and 1 to order n.
N times.
And yeah, exactly. But here sigma star is the union of from 1 to this. It should be infinity. All the possible length of the code. Okay, it can be infinity also. Okay, so we have the code. So we take each value of x and encode it to some symbols from in sigma star. So for example, in binary code, so C in binary code, so C is just the map from X to 0 and 1. Okay? To some possible string of zeros and ones. And we have the decoder, right? First of all, we encode our message, and then we want to decode it from the code. So we have the decoder. Again, is a function, is a map from our code, from sigma star to X again. Is it clear? So just let's write it. So we have X, okay, a message, and it has some distribution, and then we encode it, okay, to the code, to C of X. Okay, we encode it by sigma star, and then we decode it to some estimation of the source. Okay, so here we decode it. Here it's from the source to sigma star, and here it's from sigma star to the source. Okay? Yes.
Lossless.
Yeah, it's lossless.
Estimation.
So we demand that this reconstruction will be that G of X of C of X will be equal to X. Okay? Because we want that it will be lossless. Okay?
Lossless is just like precise.
Yeah, this is the definition of lossless. Okay, so lossless. This is the definition that if we, for any x that we take, if we encode it to something and then we decode it, we will get again exactly x. Okay? Good. Now, now we can look on the. So of course that we can, if we don't have any restriction on the length of the code. So we can take every each symbol in X and just code it with the same symbol, or just a map from a one-to-one mapping from this symbol of X to sigma star, right? Because we don't have any restrictions, so we just take, for example, if we have, I want to encode, I don't know, for example, a symbol, a string of 0 and 1. So just take the same string and encode it with by the same string, and then trivially you will not lose any information. You will not lose anything, right? But in general we have some restriction, and this restriction is the length of the code. Okay, so we say the length of the code, so L of X, X is some instance of something that we want to encode, is just the length of the absolute value of the magnitude of the code. So for example, if C of X is equal to 0, 0, 1, 1, 0, 0. What is L of X? 6, right. So L of X is equal to 6. Okay? And what we really want is that in average the expected length will be small. So the expected length, okay, the expected length is just the average over all the possible x, p of x, L of x. Okay? And so we want that this term will be as smaller as possible. Okay, so we want the shortest description of the sort. We want to compress our source as much as we can. Okay. Now, so let's see some example. Is it clear? Now, for example, we want to encode the message if it's sunny, cloudy, or rainy today. Okay, so the message. So the message is sunny, cloudy, or rainy. And the probabilities is half and 1/4 and 1/4. Okay? Now let's consider three types of codes of a binary code. So we have here sunny, cloudy, and rainy. And this is, so we have three types of code. So in this type, in C1, okay, if I want sunny, I will encode it as 0, cloudy as 1, and rainy as 1 also. And in C2, sunny will be 0, cloudy will be 1, and rainy will be 0, 1. And in C3, it will be 0, 1, 0, and 1, 1. Okay? Now, what is the length, the expected length of the first code? Right. It's 1. So, what is the expected length of all the others? So L of C1 is 1. L of C2 is
1.25.
yeah, right. And C3 right, 1/2. Okay, so of course, if my only goal is to find a code with the minimum description length, I will choose C1, right? Because it has the minimal length. But what is the problem with this code?
No unique decode, right?
It's what?
No unique decode.
It's not unique, right? It's right. You lose right. You lose information because I don't know how to distinguish between rainy and cloud. Okay. So we have these two code. Now let's think what. Now I have a slightly different goal. Now I want to give a weather forecast about the next few days. Okay. So to do it, we will say that extension of the code is a mapping from x n now to sigma to the square. Sigma star. So, okay, is a mapping, and what is exactly this mapping? Is just a mapping that takes n messages, and that this mapping is just the probability, not the probability, the multiplication of the individual messages. Okay, so now I have a code, and I want to say, and I want to know how to encode n messages. So basically, just encode each message separately and send them like this. Okay. So if we are going back to the example of for this example, now let's encode. I want to encode, for example, the forecast for 3 days from now, and Okay, and I want to encode, so now x to the power of 3 is, for example, sunny, cloudy, and rainy. Okay? So how I need to encode, I need to encode it by C2 code? Right. So C x will be 0, 1, 0, 1, and C2 and C3 will be hmm?
0, 1, 0, 1, 1.
Right. 0, 1, 0, 1. Okay? So who gives me the shorter code in this case? C2, right. But what is the problem with C2?
No prefix code.
It's what?
No prefix code.
Right, right. What does it mean? It's not unique, you mean, right? Because for example, okay, so so if I have let's define it formally. So we say uniquely decodable code is when I'm taking two messages and the code of these messages cannot be the same one if they are different. Okay? So we say that uniquely decodable code decodable, that if I have x1 to xn, some message, and x prime 1 to x prime n, if they are not equal, then c of x1 to xn is also different. Okay? And a prefix code is that if no code work is a prefix of any other code word. Okay, so in this example, so C3, right? C2 is decodable but not prefix, but C3 is prefix. Okay? Because I cannot. So for why C2? Okay, so why C2 is not prefix code? Right, because if I have I don't know to distinguish. I need to wait until I get all the message till I know what is the message.
And you still might not know, because here in C2 you don't know how to parse it.
Yeah, right. Now, for example, if I have the code 0 and 0, 1, what is the code? Is it prefix? Is it uniquely decodable? It's not? Yeah, right. It's uniquely decodable because you cannot. What?
It's a suffix tree,
Right.
right?
It's not prefix, but it's uniquely decodable because I don't have any ambiguity because well, it doesn't matter what in what order you will give me the message. I still can separate them perfectly, but I need to wait till you will give me all the code, because if I will see 0, right, I don't know if it's this or you didn't send me the 1, so it's this message. Okay, is it clear? Good. Now, so what we really want to find a code, a prefix code that has a minimal length, a minimal expected length. Okay. Okay. Yeah.
Does it matter if you try to find a prefix or suffix code, or will the minimal one always have the same length?
Again?
Does it matter if you try to find a prefix code or suffix code?
Why you want a suffix code?
Sally said that they both are uniquely decodable.
Yeah, right.
And is the minimal length of both of them the same?
For two different codes? I didn't understand your question.
Yeah, like we're trying to find now a prefix code.
Yeah.
It's going to be uniquely decodable, but we couldn't try to find the suffix code.
Right.
So does it matter which one we try to find? In
Uh,
terms of the length of the code?
No, in general. Okay, so now let's talk about bounds of the length of the code. Okay, so Shannon tells us that the expected length of the code must be at least the entropy of the source. Okay? For any uniquely decodable code. Now, of course, that if you don't have, your code is not uniquely decodable, so you can, of course, you can do anything you want.
The average, right?
What?
Write it with a capital L, then the average length of the code, right?
Yeah, exactly. Capital L is the expected length of the code.
And is the base of the log B in the entropy?
Yeah, it's log. Yeah, you have here D. You're right. You every time that you are talking about, of course, that you're talking about entropy of something, of code, so you need to. Yeah. Okay, and you saw in class the Kraft-Macmillan inequality that, let's write it. So Kraft-Macmillan basically say that if you have some number, some length of code works of uniquely decodable code over some DRA code, then you can bound the length of them. So if I have L1 to LM length, code word length of uniquely decodable code, then I know that their sum, or the sum over D minus L I is not greater than 1. Okay? And it's if and only if. If you tell me that you have some numbers, some L1 to Lm numbers, okay, I can build a uniquely decodable. Sorry. So if you have these numbers that satisfy this equation, this inequality, then I can build a code, a uniquely decodable code with this length. Okay?
Li is the length of the object I in your source?
Yeah. Exactly. And as I said, it's also in the opposite direction. If you have a uniquely decodable code with this length, I know that it satisfies this inequality. Now, so now I want to show you. I will show you. Yes. What about? What about? Prefix. Yeah. Now I will talk about prefix code again. It's also true. Great question. It's also true for prefix code. Okay. And I will show you why. We will prove it. So the first direction, right? The first direction of this inequality is trivial immediately, because any prefix code is also uniquely decodable code, right? So you just need to. So it must satisfy the inequality. Okay. Let's see now the other direction. Is it clear why the first direction is immediately? Okay. So every prefix code is uniquely decodable, right? Now we say that uniquely decodable code satisfies this equation, this inequality. So every prefix code also satisfies this inequality. Okay? Good. Now, so this is the first direction. Yeah? It's just logic, because every prefix code is uniquely decodable. Every uniquely decodable satisfies this inequality. So of course that.
We're assuming the general inequality.
Yeah. Okay. Now, how much time do we have? Okay. So now let's prove the other direction. So we will prove that if L1 to Lm are code word lengths, such that their sum of we are going to talk about a binary code just for simplicity. Okay, so if their sum, the 2 to the L minus Li, is smaller or equal to 1, then there is a binary code, binary prefix code with this length. Okay? Now, and the way that we are going to do it is just actually to build this code. And we will do it by to build or to trim a tree, a binary tree. Okay? So the general idea is this. First of all, let's assume that all the lengths are are sorted. So L1, L2 to LM. Okay, it doesn't matter anything, right? It's just name. And now we will construct a prefix code from a binary tree. So the general idea is that we have a tree.
So that if this equality holds, then the code is.
Then I can build a prefix code. There is some prefix code.
Because you didn't complete the sentence.
Yeah, right. Right, sorry. Right. So so if this holds, then there is a binary prefix code with this length. Okay?
Doesn't have to be prefix code, right? It's just one example.
No, I want to prove that. Okay, I want to prove that Cross-Macmillan holds also for the prefix code. Okay.
It's an example of uniquely decodable code, right?
Yeah. So no, but so this what gives you, because it's a specific example. You the first direction holds, but you want to prove that it's if and only if. No one says that, okay, you have this, so you can build a uniquely decodable code. But no one tells you that you can also build a prefix code. Okay? It's true in the first direction that if you give me a prefix code, that because it's exactly. Okay, but I want to prove the if and only if. Okay. And how much time do we have? So the general idea is like this. We will build a tree. Let's start with some tree. Okay, a full binary tree. And this tree will have the length of the tree is LM. Okay, as I said, we sort the length that LM is the biggest length. Now let's start with full binary tree. How many leaves I have in this tree? Yeah, but in general, it's LM. Right. It's so the number of leaves is 2 to the power of LM. Okay. And what I will do is to construct a code in this case. Let's take the first. Let's take L1. Okay. And choose a node in the height of L1 and then we move all the subtree from this node to the list. Okay, so for example, if this L1, the height is this, I will choose this node, and I will remove all this subtree. Okay, and what I'm saying that this will give me the code that I want. Okay, so if you will go, so example, the code, the first code word is, so if you have it 0, 0, 1, 0, 1, so the first code will be 0, 0. Okay, and then if so for example, if I'm choosing L2 now, and I taking, so if this is the height of L2, now I'm choosing, for example, this node, and I'm removing all the subtree of this node, and I'm decode the word in the size of L2, in the length of L2 as 0, 1, 0. Okay? Is it clear, the general idea how I'm building the code?
I feel like the logic is more like the other way. To say that this is the perfect code, and then you know the length satisfied is more than.
No, I'm building. Of course, that this is a perfect code. Okay. Now we need to prove that. Oh, so okay. No, just a second. Now we need to prove that it's really a code, a perfect code, right? Because I know this. Now I want to build a code. Okay. I want to build a code, and I need that two things: that the code will be perfect, and it will satisfy, and the length of the code words will be L1 to LM. Okay? Now, of course, that in the way that I'm building it, the code, the length of the first code word is L1, right? And the length of the second is L2, because that's how I'm building it. Right? And
it's not the most efficient tree. Right?
What?
It's not the most efficient way to build this tree, right? I mean, just one example.
It's a way to build a perfect code that satisfy with this length.
Okay, but it's not the most efficient.
No, I didn't tell you anything about the efficiency of it. But I don't need to prove the inequality, to prove the Kraft-Macmillan inequality. I don't need to, it didn't say something about the efficiency of it. Yeah.
So you say you rank the length of the code, and you put the equality to the tree, right?
Yeah.
Yeah, but I mean, if two lengths are the same, so I can flip the order, or it's method, or
If you have two the
two
same.
codes then are the same length.
Yeah, it doesn't matter. Just pick one of them. It doesn't matter. Just pick the first one, and then you can switch. Yeah.
But in the tree, they are also the same length.
Yeah, it's okay. Now okay. It's a good question, because now I need to show you a few things, right? First of all, that we basically removed how many leaves we removed in this process, okay? Because we have 2 to LM lifts, and I want to prove that that I can find a node in each length. I can find a node that even after I'm removing all the subtrees, I still have I still have a node. Okay, so for all, let's write it maybe more formally. So for all k from 1 to m, okay, I can find such node that at depth Lk. Okay? Is it clear? Because if I don't have, for example, you can think, what?
You can find the leaf.
No, because how I'm building the code, right? I'm picking some node in length Lk, and this is the code for the k word, right? Now, so you can think of it as, for example, if you remove all the, if you start to remove, you remove some part of the tree, and in the Lk, when you come into the k word, you will not have any node in this length. So what you need, what you can do, it will break the.
You mean that you want to prove that you can do this process?
Yeah, exactly. That I can do it. I'm not cheating you, basically. Is it clear? That again, that I can find such node that will satisfy the process that I just told you.
And that's how you build the tree in the first place. Obviously you can.
Why?
Because that's how you build the tree. You build the tree according to the length that you...
No, I didn't know.
You go like from L1 and then...
No, just a second. I built the tree. I didn't do anything. I built the tree. I just tell you I'm building a binary tree with this length, with LM length. I didn't build it. You have a lot of you have a lot of length that I didn't tell you what to do with them. I didn't insert them to the process of building this tree, right? I just take the largest length and build the tree. I didn't have any of these lengths.
But if it's the largest one...
Yeah. You are right. Intuitively, you're right, but you need to prove it. Intuitively, exactly, you're right. But you need to prove it. Okay. So let's start. In the case when I'm try to encode the k code word. Okay. What is the length? What is the length of the subtree from? So, for example, this is. Let's do it. Okay. So, for example, what is the length of the subtree? So, if this is Lk, okay. Now this is the length of, I'm in the k code word. What is the length of the subtree of this subtree? Right. And how many leaves do I have in this subtree? 2 to the power, right? So I have 2 to the power of Lm minus Lk, right? This is the number of leaves that I'm removing from the tree in each iteration, in the kth iteration, right? Good. Now, let's do some do that time. This is k. This is the k iteration, and this is the Lm. It's the biggest length.
Yes. I mean, it's 2 power of m minus k or 2 power Ln minus Lk.
Lm minus Lk.
Why no m minus?
What?
No, no. My question is, why no is 2 power of m minus k?
What is m minus k?
Uh,
M is the index. M and k are indexes. L is the length. Lm and Lk is the length.
but
Are the length.
but you build a tree. I think it's based on the index, right? The diff is
Yeah. Let's go to break and come to me.
okay.
Yes.
So this
This is the height of this tree is Lm. The height of this tree is L. Sorry, not yeah. The height of this is Lk. Okay.
okay.
Now I want to ask what is the height of this tree? Of course, it's Lm minus Lk, right?
Yeah,
I
yeah,
think
yeah.
it's also true to write it as you want. I think it is. You want to say like basically right. And
I think the laws have the confusion.
No, but it's not true.
No, 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 no.
Why
No,
not?
Because
m
look,
minus k.
I think the source of the confusion is that any two, like the three paragraphs shouldn't have to be related.
yeah, exactly. So, for example, Lm can be 40 and Lk can be 10. And M can be 5 and K can be 3.
Like the length of the word can be like 1, 2,
This is the
5,
length and this is the index.
can be
So
word
in this
without
example, for example, I have the length, I don't know, 2, 4, 10, 50, and this is the length. This is L1, this is L2, this is L3, this is L4, and this is L5.
Yeah. Okay. So if this is the case, so L1 L1. So this is L1, right? So so you work in this direction. So you put L1 here, right?
Right.
So this is represent this one, and L2 is 4. 4 is this one.
No, so in this case, just to be clear,
what are these numbers?
these are on the length that I want.
Length of what? Like
Of the code. The length of the first code word is 2. I wanted the length of the first code word will be 2. So I'm taking this root. Okay. Now I'm doing so. This, for example, I'm doing it. I'm saying that the first code word is 0, 0. Okay? And then I'm moving on. Now I'm going to the second, it's 4. Okay? So I'm saying, okay, so let's go to the 4 level. And now I'm taking this node will be
it would be 1 0 0 0.
yeah, exactly 1 0 0 0. This will be the second form.
Just a second.
Yeah.
What about this one? So you remove this one, or
I didn't do anything to this one.
You can just not use it.
so you just remove this one, but
Yeah.
you keep this one.
Basically, if you really want to know that if you have quality here, then you will use all the labels.
Okay.
If you have equality here, I can promise you that you will use this one.
Okay.
But in general, no.
Okay. But
העליתי.
בחצי הקודם אולי? בקודם כאילו?
לא, העליתי אחד חדש, 9. כן.
Okay. So for this case, it's like this, and keep this part, right?
Yeah, you don't care about this. I just want you to build the code, the perfect code.
Okay. I misunderstood it. So I think it's always like this. Always.
Yeah.
Always. Okay.
Okay?
Yeah.
Great.
And one more question.
Yeah.
So about the case, about the example you give before.
Yeah.
So sunny, cloudy, raining.
Yeah.
So you separate them one by one, right?
Right.
But I mean,
But you don't know. You don't know they are separated because you're getting this. You're getting zero. Think of something that you're saying. So you're getting zero. Okay. So is it separate or not? So now you get one. Okay. Oh, now you say, oh, so it must be sunny. Or maybe no. So now you get zero. And now you say, well, this is sunny or cloudy?
yeah. So what you mean? No common.
Yeah, exactly. No comment. There are no separation between them.
Yeah. Okay.
Okay.
That's not my question. Sorry.
Okay. Yeah.
So I mean, you have a sunny, cloudy, and raining, right? So
Yeah.
I mean, if you want to encode the weather of Saturday,
Yeah.
so like X3, so maybe sunny, cloudy,
Right.
raining.
Right. Right. It can be anything.
Yeah. So but I mean, you 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 encode the weather of each day by a specific colon, right? But
What?
no. My question is like, can we encode the weather of 7 days together?
This is how you do it.
Uh,
Here.
no, that's no my question.
Oh, okay.
I didn't explain very clear. Yeah. So this is sunny, cloudy, raining, right?
Yeah.
Yeah, I mean, for example, raining always follow with raining, right? Or cloudy, right? It's the probability of raining followed by raining is higher than raining
Okay. Yeah. So
followed
you
by
say okay.
sunny, right?
So you say if I know something about it, yeah.
Yeah. So the probability is not about just sunny, cloudy, and
No,
raining.
here I'm thinking as I maybe I didn't say it. My we are assuming that they are IID.
Okay, the ID.
Okay. And then if they are IID, so getting rainy after rainy is the same to get rainy after cloudy because
Okay.
they are IID.
Okay.
I say.
Okay. But I mean, if it's no ID, is there any way to do it lossy coding?
There, there is no. If you're talking about probabilities, you don't have. It must be Ludi. Ludi coding.
Yeah.
Because probability you can get something like this or something like this.
Yeah.
Here you don't have any probabilities
Okay.
about. It's not probability. The probability is about. No. I need to be more clear. When I'm saying
So what you mean is ID, but I think it's like a Markov trend.
no, it's not a Markov chain. They are ID. It's stronger than Markov chain. I don't depend in the last. I don't depend in the last message in the last message that I send you. In IID, I'm depending only.
So
In IID, in Markov chain, you say I'm depending on the previous message,
yeah.
right? But here I'm telling you, no, you don't depend on the previous. You don't depend in
Yeah.
anything.
Yeah. Yeah.
Everything is independent.
Yeah. But my question is like if they're independent, I
So
don't.
your question is if they are dependent.
If
right?
they're dependent, is there any way to do lossy coding? So like
No,
maybe.
you don't have to. You don't have a way because you're talking about probability.
Okay.
Okay. But
Yeah, I mean maybe I can encode ring together, so and I know.
no, but if you know for sure, yes.
Yeah.
But if you need to know for sure that a rainy day will be after a rainy day. That if you have some guarantee that that if you saw a rainy day, the day after it will be rainy also, then you can say, okay, so let's compress it, like send it together.
Pretty near like China.
Okay.
Okay, but in general, but if you have some probability, so you say, okay, maybe will be in 90% will be rainy, but if not, so your encoder is not true.
Yeah, but I can also encode the others, right? So but give them longer length, right? So I mean, ring have a high probability. So I give it less length, and maybe ring sunny have a lower probability. So I give it long.
You're right. It's a good point. Yeah. If you say okay, if there are no IID and you can, yeah, right. If you know, you're right. You can think of it as yeah. If you know a probability of sequences, then you can thread your message as a sequence.
Yeah.
Okay, but then you can do it, but it's difficult because it should be they should be equal in the length. In the like you cannot say there is you can, but it will increase your code. You cannot say okay, now this is a code for 2 days. Yeah, you can do it. But, so for example, rainy, right? So it's something like 0, 1, 1, 0, something like this, and raining is 0, 1, 0, 0, and stuff like this. You can do it, but you need to make sure that it's uniquely decodable, and if this has if it has it make it complicated, more complicated. But you can do it. In general, yeah, you're right. You can do it.
Yeah,
but
is there any material doing this thing? So like maybe I can read.
Yeah. Basically, you can do. We'll talk on Huffman code. Huffman. Yeah, we'll talk about Huffman code, and you can construct it by regular Huffman code, but you just need to make sure that. What is the problem? So you have, for example, still rainy, right? You need to. We want to find the. We want to find the probability of two days. Okay? So you have the first day and the second day. Now you can say, okay, so the probability, it's not the probability of rainy, it's not the probability of raining, it's not, it's something else. Okay? Now you need to define all the other probabilities, rainy and cloudy, probability of cloudy and rainy, probability of sunny and rainy, all of this, and you need to sum them to and they need to be summed up to 1, right? And then give them some probabilities, and then just build Huffman code. Okay? You can do it. It's just more complicated because you're not assuming this, so you need to define explicitly all this. Okay?
Well, thank you.
No problem.
זה נורא כאילו פרובינציאלי. אבל כשקומיקאי עושה את זה, אז זה כאילו מראה על זהו,
Okay. So before we saw a method to build prefix code, to build such code. Now let's start with some sanity check of this method. So how many lists we totally removed in this process? Okay, so we saw that in each iteration we removed two to Lm minus Lk list, right? Right? Good. So in total, how many leaves we removed after the whole process?
Over K.
Right. Sum over K. Right. K is from 1 to m. Okay. Now, this I want to see that we didn't remove too many leaves. That we didn't remove more leaves than 2 to the Lm. So this is equal to 2 Lm sum over K from 1 to m to Lk minus Lk, right? Just I just went outside the 2Lm, and this we know. What is this? Right. Right. So we get that in total removed less or equal to 2 to the Lm leaves. But we are okay. We didn't remove more leaves than we have in the tree. Okay. Now we want to the only thing that remains to show that that in each iteration, in the kth iteration, we can find a node at depth Lk even after removing all the subtrees that correspond to the previous iteration. Okay. So how we will show it? So let's assume by contradiction that when we reach to the Lk level, there is no available node at depth Lk. Okay, we don't have a node to choose. We cannot choose any node. So what does it mean? It means that that all the nodes at this level are already removed. Okay, or I'm using this node. So this summation. So let's see. So if I'm summing from I is equal to 1 to k minus 1 to the Lk minus Li. Okay. This is all the nodes that I already. This is all the leaves that I already removed. Okay. And because I don't have any nodes in the Lk depth to choose, that means that I don't have any. That I already used all these nodes. That means that I already removed at the first k minus 1 iterations. I removed 2 to the Lk nodes. Right? Right? Maybe again. Okay. Okay.
Could
Yeah.
you explain why it's Lk and not Lm?
Because now I'm looking. Okay. Now you're looking on the node. Let's. Okay. Now I'm. Let's do it. Now, for example, I'm here. Okay, I'm in this level. I want to choose a node for this code word. Okay? And the problem is, let's assume that I want to show that that you always can do it. You always have a node in this length. Now, let's assume that you don't have node in this length. Okay? What does it mean? It means that you already or remove all the nodes, or you already choose, or you already choose them. Okay? Is it clear?
Yeah.
Good. Now let's see. Okay, now let's ask what is the number of nodes that I removed from the k layer, from the k level in the previous iterations. Now, what is this number? Is exactly the number of leaves when. So you can think of it as I have the now my tree is only at LK level. Let's ignore all this, all the subtrees that behind this level. And now I want to ask. So what does it mean? It means that I already choose all the leaves of this subtree, right? That I chose in the previous iterations all the leaves of this subtree. So now I'm deleting all this, and I'm looking on this tree, and if I chose all the leaves, I don't have any node to choose in the k iteration, right? Good. Now, so now in the I iteration, how many leaves I removed from this tree? We already did it. It's 2 to the lk minus li. Okay? Is it clear? Good.
What is the I?
It's the previous. Now, okay. So I is all. I'm running on all the previous iterations. I'm in the k iteration. So it's the LK level, and I want to see that in all the previous iterations, I didn't remove. I want to see that I cannot remove all the leaves from this tree. Okay, so this is how many leaves I removed from the previous in the previous iterations.
Until the previous
What?
iteration.
What?
The level of leaves removed until the.
Yeah, till the exactly. Okay. Now, so if I assume that by contradiction that I don't have any nodes or lists of this tree to choose, that means that this summation is equal to 2 to lk, right? Because I don't have any list to choose. Now, but if this is true, so if I'm dividing it by 2 to lk, I'm getting that this summation 2 to minus li is equal to 1. Okay? Now let's see what is the summation from I equal to 1 to k of 2l minus li. What is this? What? It's larger, it's right. Okay, but so this is equal, so but what is, it's equal to 1 plus 2 minus lk. Right? It's clear? Good. But why this cannot be?
Because if you take k to m, then you get an solution.
Because?
If you take k equals m.
You don't need to take k equal to m, because they are all positive. 2 to minus li is positive. So this, what? So yeah, if you adding more terms to the summation, you can only increase it. Okay, and it's by contradiction to our assumption that that the summation of all the levels is smaller or equal to 1. Okay? So it cannot be that I don't have any node to choose. All the time I will have some node to choose in each level. Okay? Just if I have, if in the inequality, in the crushed inequality, I have if it's equal to 1, if the summation of 2 to the power of minus Li is equal to 1, then I will choose all the leaves in the tree. Okay, I'm not proving it to you, but basically you will choose. You don't have any leaves that will remain without a code word. Okay. Good. Question? Now let's talk about Shannon's code. So so basically Shannon's code. Now I want to what he says that if we we know that if we choose Li to be the log of 1 over p of I, right? It will be, we will get the best, we will attain the best entropy, the lowest entropy bound. What is the problem? Why I cannot choose for the length of each of the code word to be log of 1 over pi? Right, right. The length must be integers, and in this case, there is a possibility that it will not be an integer. And basically, Shannon code is it's very simple. Just rounding up the probabilities. So take Li to be equal to round up the probability of 1 over pi. Okay. Now, why there is a prefix code for this code? Let's prove it. Okay. So how can we prove that there is a prefix code? We can, if we will prove that the what?
You want us to show that the crossing is
Exactly. If we will prove that the summation of 2 to the minus Li is smaller or equal to 1, then we will have then we will show that it satisfies the Craft equality, and we have a prefix code. So this, okay, so this is equal to sum over all the possibilities to 2 to the Li. So we say that Li is this term, okay, minus log of 1 over pi, and we know that this term is smaller than the probability without the rounding, right? So smaller or equal, of course. So this is smaller or equal to sum over all the possibilities, 2 to the minus log 1 over pi. And what is this? What?
It's sum over pi.
Exactly. It's sum over pi. And this is equal to 1. Okay? So it satisfies the crafting quality. What is the expected code length of this? So let's show it. So the expected code length is just sum over all the possible x log of 1 over px, round, and the rounded version of it. And this, we know that it is smaller than sum over x px log of 1 over px plus 1. Okay? Of course, we just round it to the nearest integer, so if we will add 1, we will get something that it's bigger. Okay? Or equal. Okay? And this is equal to the entropy plus 1. Okay? So we get that, so the code, if we know P, if you know the distribution, right? If you know the distribution, so our code is between the entropy and the entropy plus 1. Okay? Is it a good bound? It's a good, the entropy plus 1 is a good one. Is a good bound. Of course, it depends, right? If the entropy is very small, so it's pretty bad. If we have something, I don't know, image, so the entropy is huge, so it's better. Okay? Okay, I will not prove it to you, but
Why is it bad?
if your entropy is really small, so the entropy plus 1 is a big difference from the entropy.
But anyway, the length can be on the integer. So
Yeah, I want to ask, what is the cost of doing this rounding? What is the cost in the expected length? So if the entropy is really small, I need to pay a lot in the expected length. Okay?
you can't have a difference that is smaller than one between lengths. Not expected.
No, but you can choose. You don't need to use the Shannon code. You don't need to round up. Maybe you find some different code. But if you will use this code, then it will be good if your entropy is bigger. If your entropy is small, maybe you don't want to use this code. Maybe you will find something else. Okay? Okay. Now let's talk about. Okay. So now let's talk about what if I have a lot of messages to transfer. Okay. What if n is really big? So it turns out that if I am in code in blocks, right? Till now I say okay, just encode each message by itself, right? Just take the whole messages x1 to xn, encode x1, encode x2, encode x3, and transfer it. Now, it turns out that if I'm doing it by blocks, taking x1 to xk, and then xk plus 1 to x 2k, and doing this by this, we can asymptotically get the lower bound. So let's do it a bit more formally. I will not prove it to you, but because we don't have time. But so now we are talking about. We want to ask. So we want to ask what is the rate? What is the rate? The average chord length per message, per x. Okay? So if y is equal to x1 to xn, okay? And we want to ask what is the average, what is the expected length of y divided by n. Okay, so what is the L C 1 over LC? Okay, what is the expected length of transfer one of the x's? Okay, is it clear, the question? So maybe I'll try it again. I have messages, okay, and I want to see what is the length, the expected length to transfer a message. Now, so we know we don't have it here, but we know that that for transfer a message, okay, if you will use Shannon coding, then you will be the rounding things will give you the entropy plus 1. Okay, your bound will be the entropy plus 1. Now I want to ask myself, maybe I can transfer the messages. I have a lot of messages. I still want to know what is the expected length of one message, but I have a lot of messages. So maybe I will, using blocks, I will transfer a lot of messages together. Okay? And apparently, that if you will transfer a lot of messages together, the expected length of each message, okay? So the expected length of each message, because I have n messages and the total expected length is L, this is then the bounds become so the lower bound is the entropy of x, and the bound from the other side is the entropy of x plus 1 over n. Okay? So instead of of constant factor of 1 bit that I have if I transfer it one by one, if I transfer it in very large blocks, I have here just overhead of 1 over n. The rounding procedure gives me just an overhead of 1 over n, and when n goes to very large numbers, effectively this becomes very small, and I'm achieving the bound of the entropy.
This is using Shannon code.
Yeah. What? Yeah, right. But now I'm asking. So this is okay. Here you're right. Here it's C basically. So this is the L is the expected length of y, and I'm divided by n because in y I have n messages. Okay. This is the entropy of X. It's not Y.
What are the blocks here? The blocks?
So n is the size of your blocks.
Each block contains one word.
Yeah.
You should have just encoded them separately.
No, each block is with n variables.
So each block is not with one word.
No. In the previous case, it's when each block it's one word.
If you have n words and each block is n variables.
No, you have. So no, you transfer it. So of course that you cannot transfer all your messages at once, practically. So you divide it by blocks, and every block, if you increase the number of blocks, then you will achieve this.
What does each block contain? Y is a block.
Y is a block, yeah.
But Y contains all the words.
No. So okay, Y is a block. Okay, you have. It doesn't matter how many. Messages, how many blocks you have. Okay, you only matters what is.
Y contains all the words and you have one block.
Right, but you don't need. But it's true also if you have one Y11, Y2, 1, 3. If you have several of blocks.
But it doesn't count as a block if there is only one block.
But you can do it for several blocks. If practically you cannot.
You have several blocks. You have one block here, but you put all the words in one block.
But you can do it for several blocks. Why here? So no, I just want to define you. I didn't say how many messages you have. I just define you a block with n messages. Let's talk about it after the class. Okay. Yeah.
The L inside is CY, right? The code length of Y, right?
Yeah.
Okay.
The expected content of right. Now, so let's talk about what will happen. What? Okay. Now let's see what will happen if we don't know P. If we don't know the true distribution, and we only have some another distribution Q. Okay. So we have the real distribution P. It's P1 to Pm. And we have some other distribution Q. That this is the distribution that we encode by it. And now I'm constructing the code. By this distribution, by Q. Okay, so Li is equal to rounding up log 1 over Qi, and not Pi. Okay? How bad we will be? This is the question. Okay? So let's see. What is the expected length? Let's try to find the lower and upper bound for the expected length. So the expected length, right, is just sum over all the possible values Pi log the rounding of log of 1 over qi. Okay? And this is bigger than pi log of 1 over qi. And this is, so I just can multiply by pi. Okay, so I can multiply pi and divide it by pi. And now, so this, so let's write it, pi log pi divided by qi times 1 over pi. So this is the DKL between P and Q. And this is the entropy of Pi, of P. Okay? And we can also take, don't have time, but we also can prove that the expected length is bigger, is smaller, sorry, than the DKL between P and Q plus the entropy of plus 1. So in general, we can see that if we have the wrong distribution, we need to pay in the distance, in the DKL between our real distribution and what we thought that we have. Okay? If these two distributions are different, we need to pay a lot. We encode the problem with the wrong distribution, and it's very far from the real distribution, so we need to pay a lot in the expected length. Okay? Let's see. So let's see example for the suboptimality of Shannon. So if we have P1 is equal to 0.9999 and P2 is equal to 0.9991, okay? And you can do the calculation, but according to Shannon, L1 is 1, but L2 is 14. Okay? And of course, it's suboptimality because we can do it in a single symbol, right? Okay. I'm doing it quick. Let's talk about Huffman code. So Huffman code, basically, if you know the real probability, you can construct an optimal prefix code. Okay? You can construct the shortest expected length prefix code by a very simple algorithm that discovered by Huffman. Okay, and the idea is just to build this tree bottom up. Okay, we start by the list, and we in each iteration we merge the list with the lowest probabilities. Okay? So let's see example. Let's consider that we have some source. Okay? A, B, C, D, and E. Okay? And the probabilities are 0.25, 0.25, 0.2, 0.15, and 0.15. Okay, these are the probabilities for the symbols. And now let's construct Huffman code for this source. So what we need to do? So as I said, it's very simple. Just take the smallest, the two smallest probabilities, and merge them, and this will be your node, your new node. Okay. So let's A, B, C, D, and E. Okay, so here it's 25, 25, 20, 150, and 150. Okay, so what we need to do? So let's take the D and E, the two smallest probabilities, and merge them. Okay? So we merge them to one node. Okay? And this node will have the sum of their probabilities. So this node will be 0.3, probability with 0.3. Now let's do it again. What are the smallest possible, the smallest values, the smallest probabilities? Right. C and B. So let's take C and B and merge them. And now this is 0.5, 0.
Why not C and A?
It doesn't matter.
It doesn't matter.
It doesn't matter. Okay. Now, what is the smallest possibilities? A and right, and this one. So we will merge between them, and then we will merge this one, and we'll get a tree. Okay? Now we can construct this tree based on this. So if this is 0 and 1, we just need to go over the list. So we have B, C, A, D, and E. Okay? And now when I want to ask what is the code, what is the Huffman code of this source, it's this. Okay? Is it clear? The problem, what is the big problem with Huffman code? That we need to know the probability in advance. Okay? We need to know the probability, and we are very sensitive to the exact values of the probability. Okay? Here we talked about binary Huffman code, but it's straightforward to extend it to some DRA prefix code, other lengths of code. I think that's it. We will not talk today about source coding, channel capacity, but we will do another lesson before the exam with questions from you. So we will find time. You want to doodle or whatever? Yeah, doodle. Okay. So we'll find time and send me questions that you want that I will answer them on the. Yeah, right. You don't have Tali. We'll talk next Wednesday. So, yeah, Tali we talk both in Monday and Wednesday. Okay. Questions? It's a good question. I don't know if it will be in the
Either the basis that you have
in the